Today we're going to look at Chapter 17. We just covered the solar system, the planets, just the planets and the dwarf planets. So now we're going to clean up with moons and other small solar system bodies. Chapter 17. And I want to share this one. There we go. And let's make a slideshow. All right. Let's see if I can move some of this stuff out of the way. Will it move over here? I think that would be a better place for it. Okay, looks like everything's recording and shared. All right. Moons, small solar system bodies. They may sound unimportant, but the moons and the other solar system bodies are essential to the structure of the solar system for various reasons. For instance, the moon for Earth is absolutely essential for maintaining the current behavior of the planet, so that it continues to be welcoming to the living systems that are already here. Without the moon, there is one school of thought that says life would not be possible on Earth. So, and of course, the other solar system bodies that we study give us clues as to the origin of the solar system. So they're not any less important than the major bodies. So let's see. That's not as good as I thought it would be. I wish there was some way to. I've got this strip at the top. Disable annotations. Well, I'll just have to deal with it. This is obviously a photograph of the Earth's moon. Moons in general, well, this is a classification. Moons are satellites of the planets. Natural satellites, that is. There are 214 of them. Actually, there are probably more than that, known for the, is it 8 planets? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, Uranus. Correct. Just checking my numbers. For the 8 planets and the 5 dwarf planets. The dwarf planets can have moons also. As of 2021. Okay, so I did check my numbers. It is 214 moons of the planets and dwarf planets. And for the dwarf planets, that includes Ceres, which is in the asteroid belt. Pluto, and actually the rest of them, Pluto, Haumea, Makemake, and Eris, are all in the Kuiper belt, beyond what they call trans-Neptunian space. Small solar system bodies. Okay, after we've covered the moons, Then we look at other things like asteroids, often called minor planets, comets, meteoroids, and even interplanetary dust. We don't even leave out the dust. We cover everything. And many of these small solar system bodies are trans-Neptunian. In fact, it's believed that the ones that do come into the solar system, except for those in the asteroid belt, but those that come in, like comets and other objects, are believed very often to be residents of the Kuiper belt, and their orbits are disturbed by some of the other planets that bring them into the inner solar system. We'll talk about that a little bit more later. And some of the moons of Saturn are believed to serve special roles in the maintenance of Saturn's ring system. In other words, they're not just out there enjoying the orbit. They're actually busy shepherding parts of Saturn's rings. Okay, we'll start with our moon, the Earth's moon. We've actually visited the moon. The first humans set foot on the moon July 20th, 1969. And I was old enough to remember that one. 1969, I would have been 16 years old, so I was in high school at the time. And Apollo 11 spacecraft set down on the moon with 2 of our astronauts. And they walked around for a few hours before they had to leave. And after that, we sent several more landers to the surface of the moon. So we haven't actually got real samples from the moon, physical samples. So what was the first word transmitted from the surface of the moon? It's a trivia question. Houston. That was the first word. The rest of it goes, Tranquility Base here, the Eagle has landed. They left some things on the moon also. Besides the spacecraft, part of the lander was left there as a base from which the rest of the lander took off. But they also left this device called a retroreflector. It's a device that uses what we've studied already in our optics chapter, total internal reflection. So the retroreflector is a collection of reflectors that use total internal reflection to receive laser signals from the Earth and send them back. So this is what it looked like, and they left that on the surface of the moon so that ground-based instruments could send signals to this device, get the signal, return signal, and they could judge distance to the moon. They could also judge vibrations that may be received by this instrument. Moonquakes, for instance. They do exist. And this is based upon that principle, total internal reflection. And this animated GIF here shows you that each one of these pockets has a corner cube in it. It's it's actually the corner of a cube. And if light comes in from one direction, it goes back out exactly the same direction. That's what we're showing you here. So one of those beams comes in, the other one goes out, parallel, just like that. It's fascinating. We can also use the information gathered from these experiments to judge continental drift on the Earth, or change in the Earth's tilt, right? The Earth is supposed to be tilted 23.5 degrees from the vertical, but it may vary some, right? Because of precession, the Earth does wobble like a top. So it may alter the angle of tilt. It can also be used to measure the gravitational constant because remember, Newton's law of universal gravitation incorporates in it incorporates in it this distance, right? The distance between the Earth and the Moon. So we can use that formula and some other calculations also to verify and refine the gravitational constant value, because that's supposed to be a constant. Okay. Based on these measurements, we now know that the Moon is on average, remember Kepler's law, all orbits, not just around the sun, but the moons obey Kepler's law also. The first law, the ellipse, all satellites orbit their central body in an ellipse with that central body at the focus of one of the focuses of that ellipse. So the average distance right here, which according to Kepler's third law would be the semi-major axis, is 384,000 kilometers, or about 240,000 miles. It varies. And we can measure that variability simply because this device is still on the Moon and working. Now we put, with our other trips to the Moon, we left a reflector each time we went up there. Okay, what else about the Moon? Well, it's the second brightest object in the Earth's sky. What's the brightest? That's a trick question. The brightest is obviously the sun. Right? But in the solar system, all other objects are bright based upon how they reflect light. The sun is bright because it makes the light. Everything else has a brightness based upon what it reflects of the sunlight. The word moon, I'm not sure, I've done some reading on this. I'm not sure whether moon is derived from month or month is derived from moon, but they correspond with one another. I guess we can accept the Old English word month. So the moon went through its phases and it would return to an original phase, starting phase, once a month. There are many primitive and modern societies that base their religious ceremonies on the cycles of the moon. For instance, do something during the new moon, right? When the moon is completely dark. In other words, it's near, or it could be covering the sun. That's otherwise known as an eclipse. Or it could be full moon, which occurs approximately midnight, because that makes the sun on the other side of the earth at noon. But the month that we live by the month that we live by in our modern society is based upon the moon's cycle, with some variations in there. We'll talk, let's see, I think we may have already talked about that, where we're developing calendars. Yeah. Calendars had to be adjusted, and the length of the months had to be adjusted so that these festivals, for one thing, religious or otherwise, would occur at the same time each year. There's some indication that the human ovarian cycle is roughly synchronized to the lunar cycle, which is approximately 30 days, 29.5 day cycle. But that varies quite a bit. 80% of women range between 21 and 45 days on their menstrual cycles. So it's kind of hard to pin that one down. So that's where the name started. So we get to name it. We got we identify the moon based on our month. So any other naturally occurring satellite of other planets, we now call moons with a little m. These are some more pictures of the moon. Actually, these are pictures that I took myself. In my youth, I had a 6-inch reflecting telescope and a camera. So I lived in Atlanta at the time, and 3 miles from downtown Atlanta. So light pollution was a real problem. So I had to limit my astrophotography to very bright objects. So the moon was a natural choice. It was easy to get reasonably good pictures of the moon from my location. This one shows you this crater here with its rays running out from it. This prominent crater, in fact, in my photographs, they're upside down. This is the southern pole, and this is the northern pole of the moon. Simply because of the way the camera worked with the telescope. And I had some close-ups that I made, and I had to take the pictures, and then I had to go develop them myself and print them. So I have my closet set up as a dark room. Well, enough of that. Okay, so since we first landed on the moon with Apollo 11, there have been 5 other lunar landings, all originating from the United States. 13, of course, didn't get to land because they had that accident. And there's a very well-made movie about that whole incident. But then 14, 15, 16, and 17 got to land. And there were other missions planned beyond that, but NASA canceled them. I think they wanted to put their money someplace else, and the public was losing interest. The flights were becoming routine, and that really is a good thing for the safety of the crew. If you know how to get people to the moon and back, and it becomes routine, well, that's a double-edged sword. If it becomes too routine, then you tend to maybe get slack on safety. But we'll talk, that's neither here nor there for this discussion. So in total, we brought back over 800 pounds of lunar material. And they're under NASA's control, and samples are sent to various laboratories around the country and the world, for that matter. We share these objects with the world upon request and upon justification for necessary research. Okay, if we use radiometric dating techniques, which we've discussed before, in this class. The rocks in the mountains of the moon are between 4.4 and 3.9 billion years old. So they're really old. They're as old as the Earth. The rocks on the plains are younger. So that means they formed after the mountain rocks. And this is critical information for understanding how the moon itself was formed and why we see it with its present appearance. There are no rocks older than 4.4 or younger than 3.2 billion years old. Right? And we gather them from numerous locations on the surface of the moon. So if the Earth is believed to be this old, 4.56 billion years old, but we haven't found any rocks on the Earth older than 4.28 billion years. Now, why would that be? Why couldn't we find, if we think the Earth is this old, why can't we find anything that old? Well, Earth is geologically active, and the rocks that may have formed at its beginning have since been covered up, or we can't find them, or they've been remixed. Right? So these are the oldest ones we can find. Whereas on the moon, the oldest rocks there, once they form, there's nothing to change them. They sit, and that's where they are. So if we compare these two numbers, the moon formed after the Earth formed. So trying to explain why that is a subject of endless discussion among astrophysicists. So what is the origin of the moon? Well, you have to consider these facts, right? When in any theory, the theory has to support the facts. That's the first clue. I mean, that's the first rule. A theory that doesn't support the facts, you just throw it out. It's no good. Lunar rocks are similar to the rocks we've obtained from the Earth's mantle. Now, what's the mantle? Remember, I hope we discussed this, but the that's not going to cooperate. The Earth has a core, right? Then it has an inner core and it has an outer core, right? The inner core is believed to be solid. The outer core is believed to be liquid and metallic, basically iron and nickel, and it's moving. So that's why we think that the Earth has a magnetic field around it, which protects it from the solar wind. But then above that is the mantle. Okay, and then beyond that is the crust. The crust is easy to sample, right? You just dig down in the ground. In West Virginia, you don't have to dig very deep before you hit bedrock in many places. But the mantle gives you a better picture of the Earth's makeup, because there's cycling between the mantle and the crust all the time. So if you can get into the mantle and sample it, then you get a better idea of the historical composition of the Earth back when it was first made, or its current composition with aging. So we have managed to drill a couple of holes into the mantle and bring back samples. Compare those to the lunar rocks, right? And the lunar rocks are similar to the Earth's mantle. So that suggests that at one time, the Earth and the moon had similarities, made from similar materials. We know that the oxygen isotope ratio, remember isotopes, they are elements that have two isotopes will have the same number of protons but different number of neutrons, and their ratio is an indicator of where they came from. The isotope ratios, the oxygen isotope ratios, indicate that the Earth and the Moon were formed at a similar distance from the Sun, because the Sun has an impact on isotopes. And the theory there is a bit beyond me to even discuss with you right now, but take it on faith that this oxygen isotope ratio is an indication as to how far the planet or moon was from the Sun when it formed. And this ratio is the same for the Earth and the Moon. So that means they both formed at the same distance. There's no water in the lunar rocks. There's lots of water on the Earth. So we have to explain why that is. We'll get to it in a minute. There's a definite deficiency of volatile elements, which indicates both the number 3 and number 4, the absence of water and the absence of volatile elements, probably means that at one time the moon was very hot and it vaporized all the water and drove off the volatile elements due to heat plus small gravity. Low gravity does not retain light elements very well. Okay, so that's why the Earth's atmosphere doesn't have a lot of helium in it, because helium is too light. It just if it makes it into the atmosphere from some source, like coming up from the ground, then it doesn't take long before it's gone into outer space. Even with Earth's gravity, it's not maintained, not retained. Okay. Now the moon has less iron than the Earth. So that's a valuable clue. In other words, if the moon had the same amount of iron as the Earth, then they would have had to been completely mixed at the beginning. And then the moon would have been separated for some way with its iron, but it doesn't have that iron. So that's an indicator of, that's a question that has to be answered by any theory that proposes an origin for the moon. So because of that, largely because of that absence of iron, the density of the moon is 3.3 grams per cubic centimeter, and Earth, we've learned earlier, last chapter, is 5.5 grams per cubic centimeter. So the moon is much less dense than the Earth. Okay. And the Earth is older than the moon. Now, I'm not sure why they believe that, but the theory is that it's 160 million years older than the moon. All right. So here's the most widely accepted theory now for the formation of the moon. It's called the Great Impact Theory, or the Large Impact Theory. Okay, if the Earth formed 450 some odd billion years ago, 4.5 something billion years ago, then approximately 160 million years after that formation process, a planet-sized object believed to be about the size of Mars, which is pretty substantial, actually struck the Earth. It didn't hit it head on. It sort of hit it a glancing blow. And what happened then was the ejection of a lot of material into space. There was a good bit of mixing during the impact. So the the types of minerals and the oxygen isotope ratio would have been established for both of them before and during the process. That's why they have similar compositions based on the moon samples and the Earth's mantle. So this is an artist's computer simulation. So here's the instant of the first impact. There's the object that hit the Earth right there. Okay, and when it did, it tore loose materials. These are not oriented properly, I don't think. Unless, okay, this object is coming in from upper right to lower left. There you go. It's approaching there, bang, and then it shears off a lot of material, which is thrown into an orbit around the Earth. It doesn't have enough velocity to escape the Earth. So it goes into a low Earth orbit, just a few hundred miles. And eventually coalesces, right, accumulates into what we now have as the moon. There's one version that says there were probably two moons that formed initially, but they were in the same orbit and eventually they coalesced. Now, the reason they say that is based upon evidence of the form of the moon now. The backside of the moon is completely different than the front side. And in fact, they have different gravitational effects. For satellites going around the moon, they feel a different gravitational pull on one side than the other. So it's believed that the probably the dark side, the opposite side we can't see, was the recipient of that other moon. Okay. So what are some general features of our moon? It's the largest moon of any of the terrestrial planets. Right? Mercury doesn't have one. Venus doesn't have a moon. Earth has one very large moon relative to its size, right? The moon has 1/6 the gravity of Earth, which is pretty big, actually. Mars has two moons, but they're very small. They're irregularly shaped. They're not spherical. And it's believed that the moons of Mars were entered Mars orbit as a captured objects, asteroids probably. Now, if the Earth's moon, if Earth's moon were on a sun orbiting trajectory, it would be considered a dwarf planet. Okay, one complete revolution around the Earth takes 29.5 days. One complete Earth day is 29.5 days, Earth days. So the moon takes 29.5 days to go around the Earth. It also takes 29.5 days to spin on its axis. So that means one side is always facing the Earth, and we never see the backside. Well, we didn't until we sent people and satellites up, spacecraft up there to look at it. Then we could get pictures from the backside. Okay, this phenomenon is known as tidal locking, sometimes called gravitational locking, or captured rotation, or spin orbit locking. Right? So what happens is the larger body slows down. Remember, systems have to maintain their momentum, conservation of momentum. So they're actually affecting each other, the moon and the Earth. And in the process, over millions and millions and millions of years, they reach a point where the gravitational pull and the positioning of their orbit is such that now they both rotate. Well, not the Earth, but the satellite rotates at the same rate as its spin. Remember our discussion of Mercury? It's almost tidally locked. It's harmonic. It's a 3-to-2 ratio. But this tidal locking occurs in several places, or near tidal locking occurs in several places in the solar system. All right. Okay, the surface features on the moon, which have been forming over millions of years, are still there. No erosion, because the moon is no longer active enough to erase them like the Earth does with its various features. For instance, if a large body impacts the Earth and leaves a crater several million years ago, then it will be covered up. It will either be covered or consumed by Earth's geologic activities. Whereas on the moon, all the craters that were there are still there, except for those that might have occurred in the plains, in those flat areas that we'll describe in a minute. So here's some characteristics of the moon. Right? It has a diameter of 3,476 kilometers, or about a little over 2,000 miles. It's about 1/4 of the Earth's diameter. Right? The Earth is believed to be about 8,000 miles in diameter. Not believed to be, it's been measured. We mentioned the average density before. Surface gravity on the moon is only 1/6 of the Earth's. Right, so I'm 210 pounds on Earth. On the moon, I'd be about 34 pounds. This is an interesting fact. The average reflectance that we call albedo is only 7%. That is, 7% of the light that strikes the moon is reflected from it. And that's because the dust, we give it a name called regolith. The dust and the rocks and so forth on the surface of the moon do not reflect light very well. So it's only 7% average reflectance. Now, this is another one of those calculations that I did just to satisfy me, to show that the ratio of the Earth to the moon's gravity can be calculated, right? We know that the mass of the Earth is 10 to the 24th kilograms. The mass of the moon is 10 to the 22nd kilograms. We know the radius of the Earth. We know the radius of the moon. So if we use Newton's law of universal gravitation, we could say, okay, what's the force of gravity on the Earth's surface? Right? Calculate that. What's the force of gravity on the moon's surface? Calculate that. And then ratio them. Well, as it turns out, we don't have to carry the calculation out to a final number, right? The mass of a person or an object on either one of these, the moon or the Earth, is the same, right? And the gravitational constant is the same. So when we ratio them, Earth to moon, those two factors right here cancel out. They're gone. And then the ratio that's left over is 6.05. So actually, the ratio of gravity of Earth to moon is 6.05 rather than 6, rounded off to 6, right? You don't have to regurgitate this. It's just a demonstration of what you can do if you're patient and you understand what the formulas will allow you to calculate. Now the mass ratio, this is interesting. The mass ratio of Earth to Moon is actually 81 to 1. So the mass of the Earth is 81 times that of the Moon. The tendency is, if you say that the force of gravity is 1/6 as much on the Moon as it is on the Earth, the tendency there is to say, well, the Moon is 1/6 the mass of the Earth. But remember, that's not the only thing that's involved. It's the distance between the center of gravity of the large object and the small object that's being measured, right? And for the Moon, it may have less mass, but you're also closer to the center of its mass. So those factors had to be taken into account to get this ratio of 6 to 1. All right, so that's the point of this calculation, is that just because the mass is this much doesn't mean that the gravitational force will be the same ratio. All right. So it's believed that the Moon has a core, has a mantle, and has a crust, right? But they're all solid. In other words, with small heavenly bodies, even if they start out molten or very hot, then the smaller ones cool faster, because the ratio of surface area to mass is so much higher, then they cool faster. You can see this in biology, right? Look at some of the animals on this planet that are large, right? This is not a hard and fast rule, but many of the animals that live in cold regions, like Arctic regions, are large. What that does is it makes smaller surface area for the mass, which means they can retain their heat better in those cold environments. Well, that's why we think the Moon is solid at its core. The other indication that it may be solid is it has no magnetic field. And you need, the theory is that you need a moving metallic core in a planet or a moon in order to develop a magnetic field. Okay, so I mentioned this one earlier. The crust of the Moon is thicker on one side than it is on the other. And they first noticed that with this gravitational anomaly. In other words, they calculate the trajectory of satellites or spacecraft based upon what they believe to be the density of the body that they're aiming for. And once they go into orbit, they find that the orbit of that satellite around the Moon is not what they thought it would be. So they do some more looking and they find out that the gravitational constant on one side of the Moon is different than it is on the other. Now, not the gravitational constant, the density, excuse me, the density of the object is greater on one side than it is on the other. The gravitational constant, G, is a constant. Doesn't have a magnetic field. Perhaps at one time it did. And besides, even if it did have a liquid core, electrically conductive core, it's not rotating. It's not rotating rapidly enough to generate a magnetic field. Not like the Earth is rotating once in every 24 hours, which means at the equator, any object at the equator is traveling about 1,000 miles an hour. So that's pretty quick and required to generate this magnetic field that we have. Now, the rocks that we brought back from the Moon do show some magnetism. That means if a rock forms while it's hot or even molten, then the potentially magnetic particles in that rock can be oriented to an existing magnetic field. We do it on the Earth all the time. You can put that piece of rock in a device and say which way, if it's magnetized in any way at all, which way is it pointing, right? So you can tell based upon its orientation when you sampled it, which way the magnetic field was pointing when that rock was formed. So there is some magnetism in the rocks that were brought back from the moon, which means at one time the moon had a magnetic field, but it doesn't have any more because we can't measure one. There's none there. Okay, prominent features on the moon. Right? We know it has craters and lots of them. In fact, it has some craters with craters in them. So at one time in the moon's history, it was bombarded. And we assume that the Earth was also bombarded by lots of objects. And the Earth since has erased the evidence, but the moon hasn't. It has basins, low areas. It has plains, wide, broad, flat areas. It has rays coming out from craters. It has rills, which are basically valleys. It has mountains. And it has faults where the surface of the moon is shifted like this. Or we can tell that it might have been shifted this way. So what is a crater? Crater is derived from the word that means bowl-shaped, which makes sense, right? Craters are bowl-shaped. Lunar craters, they run the gamut. Large, small, all sizes. And they're believed to have been formed by meteorite impact. Okay? For individual craters, the volume of the rim and the crater are about equal. Right? So if you make measurements and you say, okay, this material outside the crater, which constitutes the rim, and then you measure the volume inside the crater at ground level, not at high rim level, but at ground level, measure the volume inside, and they're about equal. So that supports, if a meteorite impacts the ground, it throws this material out, and we account for all the material that's thrown out as missing from the bowl. All right. We can see about 30,000 craters from the Earth using telescopes, but there are a lot more on the other side. In fact, many, many more than 30,000 on the side we can't see. They range in size. Some of them are hundreds of kilometers across, and those are easy to spot from the Earth. The shapes of the craters do change a little bit based upon their diameter. There's some correlation there. A kilometer-sized crater will be smooth bowl, smooth interiors for the bowl. If it's greater than a kilometer, it has a flat interior. So we have a smooth bowl shape for kilometer sized. Greater than a kilometer, we have a flat interior, which tells me that when the strike occurred from the meteorite and blew out material, there was so much energy there in that impact that material was melted. And melting material, like water, seeks its own level, and it became flat before it solidified again. Greater than a kilometer is flat with a central peak. Now, if you've ever seen slow motion photograph of a water droplet striking a body of water, a calm body of water, you'll see the water flare out like this, and then it'll come back and shoot up in the middle, forming that peak. Well, that's basically what happens with these large craters. The impactor is so huge, the meteorite is so huge, that not only does it melt the crust, but it also rebounds to form the peak. Okay, this is a crater field on the moon, and we have the light's coming in from an angle, so it looks like it's coming in from the left of our view. So you can see some of these large craters with flat surfaces, and then a central peak. And then this one obviously should have come all the way around like that, but later craters smacked into it, like this one, this huge one, made a flat one. There's a central peak here, but it kind of got messed up with this impact. And then there are these smaller ones, and they're perfectly bowl-shaped and smooth. Okay? Okay. This time of intense meteorite bombardment occurred very soon after the moon was formed. Right? So what that means is that the interior of the moon was probably still liquid when they impacted. So not only could the energy of the impact liquefy some of the moon surface, but it could have punched far enough through the crust to reach the liquid interior and let it come back out. So after about 3.1 billion years, the moon had cooled enough that 3.1 billion years ago, the moon had cooled enough so that molten rock could no longer get to the surface. Right, I already said this before. So it's believed that the moon has been geologically quiet for that length of time. Over 3 billion years, it's been quiet. Now, what are some of these other features? The lunar plains, often called maria. Maria is Latin for seas. They look like oceans. And they were named by Galileo. Right? He pointed his telescope there and figured, well, nobody else is looking at the moon, so I get to name some things. And with his drawings, his drawings of the moon, in fact, that's an interesting story. The telescope that Galileo built himself, he ground the lenses and made the telescope himself, had a very narrow field of view. The magnification was so high that he could only see part of the moon at a time. So he would draw what the parts he saw, and then he would shift his focus, his vision, move the telescope to another part, and he'd draw that on the page. And then there'd be some overlap so he could fit them back together. So he pieced his drawings back together like a jigsaw puzzle, and then redrew them as a complete picture of the moon. Okay, these lunar plains, they're generally very large. They're darker than the surrounding material. And obviously, they're flat areas. They're believed to be, one theory is that they're craters formed by meteorite impact that then filled with volcanic lava. They'd have to be pretty big impacts because these maria are large areas also. But apparently the rising volcanic lava filled in the maria and left very low ridges around the outside. They're dark in appearance because the flat plain areas reflect even less light for some reason, they reflect less light than the other features on the moon. So their localized albedo would be less than 7%. Okay, the moon is covered by this regolith. Rego refers rock. No, lith refers rock. Rego is a blanket. So it's a blanket of rock. But it's very powdery. It's very fine. And if you look at it under the microscope, it's very angular. Very sharp. So if you breathe that stuff in, it can damage your lungs. Because it just tear them up. It's like shards of glass inside your lungs. The rock samples that we examined were similar to volcanic rock on Earth. So that's another way to get a sample from the mantle. I should have mentioned that earlier. We have drilled down to the mantle and gotten direct samples, but the lava that comes up from a volcano is actually a sample from the mantle. So those magma chambers that fill underneath a volcano are filled from molten rock from the mantle. And those rock samples from the moon are similar to our volcanic rocks that we obtain on Earth from that source. Okay, let's see. Yeah, lunar plains. We're still talking about lunar plains. Major eruptions. So early in the moon's history, it was extremely geologically active. Now, these plains are more common on the near side of the moon than they are on the back side of the moon. So that's one indicator that the back side of the moon has a thicker crust than the front side. Because otherwise you'd see plains on the back side of the moon too. But the lava couldn't get through the thicker crust to erupt on the surface, so it came out the front side. Now, how do these rays form? Well, first of all, let's characterize them. The rays form radiating from craters. They're thought to be pulverized rock that was just thrown out from the crater when the meteorite struck, which makes sense, right? The simplest explanation is usually the best. Until a better one comes along, and we're going to go with that one. This material, though, is much brighter than the surrounding material, and material from the crater as well. Powdered rock reflects more light than regular sized rock. Right, smaller particles are more efficient at reflecting light than big chunks are. Sometimes, if you follow the ray out from the crater, the impact crater, you'll find tiny craters adjacent to or within the ray. That's believed to be larger pieces of debris that flew out and struck the moon surface again. Now remember, the moon only has 1/6 gravity of Earth. So when these impactors hit, material is thrown much higher than it would be on the Earth. So it goes way out, away from the impact site. This one crater that I showed you in my photograph is called Tycho, after Tycho Brahe, the astronomer. We talked about him and his relationship to Johannes Kepler. This is the most prominent ray crater on the moon, and it's massive. Look how far those rays go. They're huge. Here's one with rays. So you can see these are a little fainter, but they're still there. I was looking for possible small craters. Maybe some of these little ones here might be associated with ray. That one could be had come out from that impact. I'm not an expert at this, so I'm just speculating. Okay, how about rills? Long, narrow trenches or valleys in the moon's surface. Some are straight, some are curved. These are thought to represent separation cracks caused by moonquakes. So the crust actually just pulled apart. Sometimes it pulled straight, sometimes it pulled crooked. We've seen these features form from earthquakes as well. So that's one of the ways that we sort of wrap our minds around features on the moon is, do we see any of these similar features on the Earth where we have a chance to study their formation? And that's one of the reasons we think these rills were products of moonquakes, right? Okay, we get some curved ones here. We get a pretty long one there. That one might even, that could be something else. But this is on the eastern side of Mare Nubium. Mare goes back to the the plains, right? The Maria. So we can say Mare something or other. We're saying that's the Maria by that name. Okay. There we go. The wall, and there the commentary here is focusing on that one right there. The wall is 113 kilometers long, right? And it's 244 meters in height. So it's pretty high. Where are the mountain ranges found? Well, the mountain ranges, some of them are up to 19,000 feet high. Pretty high. Where do we find them? All the mountain ranges appear to be formed in a circular pattern bordering the lunar plains. There's a key. If the mountains are bordering the lunar plane, that's one of the reasons that the researchers believe the plains were formed by impacts, massive impacts that formed the rim around the crater, but they accessed the molten mantle of the moon, and it flowed out and filled up the crater. And these mountains were left behind. So those impacts must have been massive. They must have been just short of moonbusters. If they'd have been much bigger, they probably could have blown the moon apart. So that's why we say that the mountain ranges on Earth are formed by a completely different process. Okay, how about faults? Breaks or fractures in the surface of the moon where movement has occurred. Some of the rills, right, there's some overlap here. Some of the rills were probably formed by faulting. And that rill we were describing earlier was probably formed by faulting in the crust. So, and since there's no erosion on the moon, once you get that fault formed, it stays there for millions and millions, even billions of years. Okay, let's talk about the motion of the moon now. The moon orbits the Earth, but the moon's orbital plane does not coincide with the Earth's orbital plane. In other words, let's see. Give me a second. I need a clean surface here. All right. So here we have the sun, and here we have the Earth's orbit. Okay. So this is the Earth's orbital plane, flat against this board. Well, the moon's orbital plane is tilted like that. In other words, the moon doesn't orbit like this in the same plane as the Earth does. It orbits kind of, it's tilted somewhat, right? It's not much, it's 5 degrees with respect to the Earth's orbital plane. So what is that? What's the effect of that? Due to this tilt, it's possible for the moon to be directly overhead at any latitude between 28.5 degrees north and 28.5 degrees south. Why do we say that? Because the Earth already has a tilt of its own, 23.5 plus 5 degrees. Right? So at any place between here, remember when we talked about the Earth and its tilt, the sun could be directly overhead between the equator and 23.5 degrees, any place in there, as the Earth moved around in its orbit. The sun could be directly overhead, any place in there. But since the moon is also tilted in its orbit at 5 degrees, then with the Earth's tilt on top of that, then the moon can be overhead at 28.5 degrees. Okay, so that's one of the effects of the 5 degree tilt. I thought I was going to introduce another statement here. It has to do with if the moon, I'll save that discussion for later. We're going to get to that. When we talk about moon phases, I think it'd be better. I'll add an item to this when we talk about moon phases. So let's move to this idea. Both the rotation of the Earth on its axis and the moon's revolution around the Earth are counterclockwise. In other words, they're prograde motions. Earth goes this way, it rotates this way on its axis, like it goes this way, and it goes this way, and then the moon goes this way. So they're all counterclockwise viewed from the north. Plus, the moon rotates on its axis counterclockwise. So we're all going the same direction, so to speak. So this is I don't know if this came out of your book or not, but it's a good illustration. It shows that here's the Earth's orbit, here's the moon, exaggerated actually, moon's orbit around the Earth, and this is the tilt. Right? So the tilt is the moon is well, actually, it depends. If it's over here, then it's tilted the wrong other direction. So for this illustration, we're seeing the Earth tilted away from the sun. So this must be winter for the northern hemisphere. And there's the 5 degree tilt. And there's the 23.5 degree tilt. So when you add those together, you get the swing from 28.5 degrees plus or minus, north or south. Okay, so they're actually 5 degrees 8 minutes is the actual tilt of the moon's orbital trajectory. So what that means is the orbital plane of the moon and the orbital plane of the Earth intersect at only 2 points, right? They intersect on this side and they intersect on that side. During the monthly cycle, of course. These are called nodes, right? When the orbital plane of the moon cuts through the orbital plane of the Earth, then it will do so at this point and at that point over there. Those are called nodes, and they have different names for each node. The ascending node is the point of crossing going northward. So on this side, this would be the ascending node on this side of the planet, where the moon, actually that line should have gone across here. And the descending node is on the other side. Moon is moving down. Ascending node, descending node. Now, obviously, and we've mentioned this type of reasoning before. Actually, it's observation. There are 2 types of lunar months, 2 different lunar months. The sidereal month is the one that's anchored to a fixed point in the sky, a star. So the sidereal star-like month is only 27.3 days. Okay, other than the sun. Right? So it rotates around, and this point right here might be facing that star. And then by the time it gets over here, right, that point has moved around to here. Now still facing that star. See? So the Earth moves over to here, and the moon's here. So that means it has not gone 360 degrees around. Right? Because it moved over here, that means now it doesn't have to move as far to point to that star. So that makes the sidereal month shorter. The synodic month, which is another word for a together path, is 29.5 days. And this lunar cycle is with respect to the sun. So if we say this side is pointing toward the sun, right? Then when it moves around here, that same position is pointing toward the sun. That means the synodic month, 29.5 days, is required for a complete 360-degree rotation of the moon. So this one is the one that's responsible for the phases. Okay? Complete 360 degrees means you're going to get all the phases of the moon with the synodic month. And that's this discrepancy between these two is why a lunar calendar very quickly gets out of sync with a sun-based, an Earth orbital calendar, right? And to make them jive, we have to do some fancy footwork. Like every 4 years, we add a day to February. That type of thing. And from the Earth's perspective, it appears that the moon rises in the east and sets in the west. Why is that? Because the Earth is moving this direction. A person standing over here will see the moon in the east as it rotates around. Okay? And the moon's not moving fast enough to keep up with the Earth's rotation. The Earth is rotating at 1,000 miles an hour, or one rotation in 24 hours, but it takes 29 and a half days for the moon to get around there. So the moon does appear to change position, each night at the same time. The moon will have moved some and changed its phase, but it always appears in the east and sets in the west. Okay. This is the phases of the moon are the moon's periodic change in appearance. Right? And it's the most outstanding visual feature of the moon is the phase it's in and the changes of phases it goes through in the synodic month. Now, why does it do that? Right? Well, first of all, one half of the moon is always reflecting light from the sun, right? So no matter where it is over here, it's receiving light. And the fact that the moon is 5 degrees, its orbit is 5 degrees off from this orbit, we don't get an eclipse every month. Right? The moon sits up here, high on this side and low on that side. So, or vice versa, depending on where we are in the orbit of the Earth. And that's why we can look at the full moon and the Earth doesn't block the light, because the moon is 5 degrees high. Okay, now occasionally, whenever the moon crosses this, let's go back. Whenever the moon crosses the node, then that puts it in position to experience, well, no, if it crosses the node, it's over here. Okay, scratch that. I was following the wrong line of reasoning. It just means that most of the time, the moon can be full and no eclipse. Or the moon can be on the sun side and doesn't block the sun because it's not in the Earth's plane of orbit. But every so often, with the movement around the sun, you get a perfect alignment between the two tilts of the Earth and the moon. And then you do get blockage of light for the full moon, or blockage of light from the new moon, and you get an eclipse. And we'll talk about eclipses in a few minutes. So, if the full face of the moon is illuminated, we call that the full moon. It's a full moon, but it's really only half illuminated, right? Right? And the half moon is only 1/4 illuminated from our position. Actually, half of the moon is always illuminated, but during certain times of the month, we only see half of that. And the other half we see is the dark side. Okay, the starting point for the synodic month is the new moon. That is when it's on this side of the sun, of the Earth, right? So the fully illuminated side of the moon is toward the sun, and the new moon we see at noon on that day, and it's dark. So the only reason you know it's there is maybe it casts something of a shadow. Okay, so here are the phases. Okay, the sun's over here. If the moon's on the opposite side at 12 midnight, you see a full moon. Whereas on the other side, the starting point, the new moon, you see nothing. Or you get an eclipse. And then as the moon moves around, it's still rotating, right? It's rotating around like that, like that, like that. So now only half the first quarter, only half of it, of the full moon, is seen. Then you go full moon, then you go around and you see the other half is illuminated. Well, actually, yes, you see the other half illuminated. If you take that one and go, if you take this, the moon here, let's see, it's going around the Earth, so I need a bigger picture here. Earth, and then moon. There we go. So if the moon is here, and sunlight is light this side, it's dark this side. Right? So you see this part. But if it moves around over here, now this side is dark. So that side is lit over here. On this side, that's dark. And this is light. Okay? It's hard to tell with this drawing because it's just a perfect circle. But that side there is now over here. Okay? So that's how you get the phases. It's observation from the Earth's perspective of light and dark portions of the moon. Now, the dark of the moon really isn't dark. So if you want to play around with a simulator for the phases of the moon, it might be instructive. Go to this website. You may have to hold down the control key when you click it. I could probably click it right now and get there because I've got this little hand. But if you don't see that hand or you don't see a change in your cursor, just hold down the control key, click it, and it should take you to that. As long as you're inside PowerPoint and looking at the slide. Okay, so let's talk about these terms, waxing and waning, and crescent and gibbous. What do they mean? The waxing phase means that the lighted part is getting larger. So when would that occur? Well, as it moves around this way, it's still, let's go back. It's waxing because the lighted part is getting bigger. From this side, it's only a quarter moon, but it's getting bigger toward the full moon. It's waxing. Okay? If it's on the other side, it's the lighted side is getting smaller. So we're saying it's waning. And it's a waning form. Right? So we need to define what our other terms are also. Waxing and waning. The crescent moon is less than half of the visible portion of the moon is illuminated. Right? So it may start out like this, but oops, wrong way. There we go. It's only showing part. That's a crescent moon. So a crescent isn't always the same size. And the gibbous moon is the opposite. More than half of the visible portion of the moon is illuminated. So we can say it's a waning crescent, it's a waxing crescent, it's a waning gibbous, it's a waxing gibbous. And the reason we apply those terms to the crescent and the gibbous is because they're not fixed sizes. Crescent varies. Gibbous varies. Quarter does not vary. New does not vary. Full moon does not vary. Right? So we can't say a waning full moon or a waxing full moon. It doesn't work. It has to be referencing crescent or gibbous because they're the ones that can be variable in size. whereas those others can't. They're fixed size. All right, so here's what it would look like if the observer is looking south, right? We're facing south, looking at this scene. Okay, overhead, we would see at 12 midnight, we would see the full moon, right? And if, which way is the moon actually traveling in the sky? It's traveling counterclockwise. If we're looking south, then the moon is traveling this direction. It's going from new through to full and back around to new, right? So it appears to rise in the east and set in the west, but the moon itself in its orbit is traveling from west to east, counterclockwise, prograde motion, right? So night after night after night, you would see the change, noon, or actually this is daylight. You would see new moon, and then you'd see a waxing crescent, then you get to quarter. Actually, wait a minute, it's moving the other direction. Hold on just a second. New moon, it's moving this way. Yes, on this, even though the moon is moving from west to east, we're seeing the moon change from new moon to waxing crescent, first quarter. So first quarter is here. So we're seeing crescents form here. So as we rotate this way, we're actually seeing the new phase as it appears here. And it seems to be moving, actually it appears to be moving across from east to west. Okay. Okay, so how long does the waxing crescent phase last? All right, think of it this way. At these four different points, we divide 29.5 by 4. Right? So 1/4 would be 7.375 days to this point. Right? So the waxing crescent would be visible for 7.375 days, or a little bit less, until it reached half moon. Then you get to first quarter, when the moon is exactly 90 degrees. Then you'd have waxing gibbous, another 7.375 days. That should be, oh, no, never mind. Less than full moon. It would take it this many days to get from first quarter to full moon. Right? It's at 180 degrees from the sun. Then the gibbous would start waning for another 7.375 days until it reached last quarter, when it's at 270 degrees from the sun, going toward the east. And then the waning crescent would take that many days, fraction of a day, to reach the new moon. Okay, we've gone 360 degrees now. Right, that's the synodic period for the moon. 29.5 days to go, 360 degrees. So this is what it would look like. Let's see. Where's the new moon? Oh, we don't have a new moon. All right, so let's start at the bottom. Right? Waxing crescent. Now, if this is in the sky and you're facing south, which way is the sun? The sun's to your right, correct? It's toward the west. So it's just appearing as the sun goes down. Then the next day, it's a little further to the east as the sun goes down. Well, first quarter. So now, it'll first appear when the sun sets. And it'll be, the sun is off this direction, like 90 degrees from us. This way, the sun has been down for quite a while. And now the sun is back kind of over your right shoulder. And this way, the sun is directly behind you. Then here, the sun, now with this moon, is off to the left, off of your left shoulder. And then this way, it's right angles off this way to the east. Okay, I've said this before, the full moon is always on the opposite side of the earth from the sun. It has to be. That's the only way you can illuminate the whole disk, see the whole disk from Earth. So what does that mean? That means when the sun is at its lowest point, let's see. I don't have a good drawing there. Let me see if I put a figure in here to cover that. Well, no, I didn't. Think about the Earth. If it's tilted this way, right, 23.5 degrees, if it's tilted this way, 23.5 degrees, that means the northern hemisphere is in winter, right? And if we're in winter, and the moon is full, that means the sun is low in the horizon. But that also means the moon has to be high, right? So if we're on this side, we see the moon high in the sky when the sun is low in the sky on the other side. That's what that means. Winter solstice, the moon will be at its highest, simply because of the tilt. And it will be directly overhead for anyone at 28.5 degrees north latitude. So if you're 28.5 degrees here, the moon will be directly overhead. Okay. Well, let's see. I didn't put in there. So if we're on the other side and we're at the summer solstice for the northern hemisphere, then the sun will be at its highest point and the moon will be at its lowest point. So it will be directly overhead for people standing on 28.5 degrees south latitude. All right, now we can talk about eclipses. Right, all the light for our solar system comes from the sun. setting aside lightning bolts and stuff like that. Every object in the solar system casts a shadow. There's no avoiding it. If the sun is beating down on one side of your planet or moon, the backside is in shadow that extends away from the object. Now, let's see. Let me clean this up a little bit. All right. So if we have sunlight coming from here, right? We've got rays like that, rays like that, rays like that, rays like that. Well, from the surface, the light's going every which way, right? And if the sun, as big as it is, it has an angular size in the sky. So if you have an object out here like the Earth, right, light's not going to just come like this. Plus it has an atmosphere. Light's not going to come out here like that and make a cylinder. Light's going to be coming in from every direction. So what you actually get is you get a, let's see. Right. And you get there we go. So you get a cone shape behind the planet. And anything that's far enough out here, beyond the cone, gets enough light from the sun. Even if they're directly behind us, it gets enough light from the sun to illuminate them. But that's the shape of the shadow behind objects is cone shaped. And it varies. It depends on the size of the object, Earth, Moon, Jupiter, Saturn, you know, asteroids, whatever, and their shape, right? If they're spherical, it would be a genuine cone. If they're oblong, then it'll be a weird shaped shadow. And how far away from the sun are they? Right? The farther you are away from the sun, the less steep this angle is. So this partially illuminated section out here is reduced the farther away from the sun you get. Okay, and I just explained why that is. Okay. So what is an eclipse? Well, the definition is it's a darkening of the illuminated portion of a heavenly body that has wandered into the shadow of another. The darkening of the light of one celestial body by another. Right. So if they happen to cross that shadow, or if they come in front of some, this way the object will be in the Earth's shadow, this way the Earth will be in its shadow. So either possibility. All right, this section right in here gets no light whatsoever. Well, let me qualify that. Since the Earth has an atmosphere, you do get some refraction. So the refraction will put a little bit of light in that dark cone, but not much. But this is the darkest area, and it's called the umbra. And this partially dark is called the penumbra. Okay. And there you have a picture from space, probably from the International Space Station, of a solar eclipse. The moon has passed in front of the sun and cast a shadow on the earth. And this section right in here is the umbra, and all of this out here is the penumbra because of that. If you happen to be standing in the penumbra section, you'll only see a partial eclipse. In other words, only part of the sun will be covered. In other words, you're off to one side, so you'll actually see part of the sun. Okay. We do have a video. So let's watch this. Here it comes. Why don't I hear the sound? I thought there was supposed to be sound with this. Oh well, the visual effect is there. It'll keep looping until I tell it to stop. But you see you'll watch the shadow pass across the earth. And that path is different for every eclipse. It doesn't just go straight across like that. It takes a different path each time, depending on where the moon is, where the sun is, in their orbits. There you go. But it always travels from west to east. Okay, let's stop that. Okay, so that was a solar eclipse when the moon blocked light from the sun. It's strange, seems odd. The moon is exactly the right size and exactly the right distance from the earth to exactly cover the disk of the sun. Their angular size is the same, with some variation because the orbit of the moon varies. So depending on if the moon is actually closer to the sun, farther away from the earth, what happens is you may end up out here. So if you're observing from here, what you'll see is an annular eclipse. If you're in this region right here, you'll see, right? So the sun is here and the moon is there. And you'll see a ring. But if you're off to one side, you'll see like that. The moon will be blocking the sun. And the moon always has to be at new phase in order for that to happen. That puts it on this side. So you actually don't see the moon very well as it approaches and covers up the sun. So here's an artist's depiction of the umbra right there and the penumbra here. Okay, there it goes. This was, oh, actually, this is a prediction. This predicts a total solar eclipse on April 8th, 2024, which is going to pass across the United States. I think it's going to be north of us. Watch it again. Where does it go? Yeah. Crosses over Lake Erie. Right? So if you want to see it, you just need to travel north a few hundred miles. But we will be able to see a partial eclipse from West Virginia. April 8th, 2024. So think about it. Why isn't the eclipse track stationary or linear? Well, it's not stationary because the moon is still moving. It's doing like that. It's moving in its orbit. The Earth is moving and rotating. So all those motions mean that the eclipse is not going to sit still. And the track depends on when is the moon at new. Well, it's at new for different places on the Earth. It's viewed from different places on the Earth. All right. So the length of the moon's shadow varies with its distance from us and the sun. Well, no, the length varies with the distance from the sun, and our distance from the moon dictates whether it's a total eclipse or a partial eclipse or annular eclipse. There's your annular eclipse definition. So we've observed eclipses, many eclipses, and we've done calculations based upon the position of all the heavenly bodies in relation to the sun. And it's believed that the maximum diameter of the umbra on the Earth is about 270 kilometers. So it's not very big. So what can we, is there a practical use for a solar eclipse? Well, yes, there is. In fact, when the moon blocks out the glare from the sun's disk, you can see around the outer edges the sun's atmosphere, the corona. And when it does that, we experience changes, momentary changes in the Earth's weather, because there's no light reaching the Earth, right? So you can do some experiments there. You can also look at the sun, how animals respond, right? If you're living on a farm, you may hear the chickens might go to roost. And then when the sun comes back out, you might hear the rooster crow. Let's see, let me hold that one for a second. You can also observe because the moon doesn't have a smooth disk surface, it has hills and valleys and mountains that you see from the edge. You can actually see the contour of the moon's outline illuminated by the corona. In the corona, you can also see other features of the sun besides just the coronal glow, but you can see prominences, which are parts of the moon's atmosphere being blown out and coming back. Blown out and coming back. They're following magnetic lines is what they're doing. Or you can see flares blast out. Okay, this is probably the most famous experiment conducted using a solar eclipse. It had been planned for many years, and the first attempt failed. But this attempt was by Arthur Eddington in 1919. There was a solar eclipse, and I think he went to some island in the Atlantic Ocean. Was the best place to observe it, off the coast of Africa. But what was he trying to do? Eddington wanted to photograph stars, the light coming from a star that was very close to the sun. The path to the star was very close to the sun. Now, why would he want to do that? Well, what Albert Einstein said in his theory of general relativity was that gravity will affect the path of light. Right? Gravity from large, massive objects like the sun, would bend the path of light. Right? So if you're here on Earth, this is the sun, and you're here on Earth, and you're observing a star, and you see the star during an eclipse. It's the only time you can see it because the glare of the sun gets in the way. You can't see the star. But you can see a sun-grazing star from Earth right here. There's your star at some distance, way, way, way. But you know which star that is because you can look at it when the Earth is over here. Right? You can see that same star. So you know where it is, where it's supposed to be. And if you see it over here, and it's supposed to be over here, that's the real position of the star. This is the observed position of the star during the eclipse. Right? So you see this star like it's as if it's over here. What's happened is the light goes here like this and is bent. And if that's true, and Einstein predicted how much bend there should be, what's the difference in the position of these two? What's the angular displacement? Right? He predicted this value, that angle. And Eddington took his photographs, and then he took them back to England and analyzed them, right? And found exactly that discrepancy. So that confirmed one of the predictions of Einstein's theory of general relativity based upon these observations during that eclipse. Okay, so these are types of eclipses. You can see the corona here, right? The sun's atmosphere. This is an annular eclipse, right? where the shadow of the moon doesn't quite reach the surface of the earth. So you're actually seeing part of the sun here. This is a time lapse of a total solar eclipse. That video only took 53 seconds, but the actual would be on the order of minutes, much longer. It was speeded up for our benefit so that we wouldn't have to sit here all day to watch it. So that was a total solar eclipse time lapse. This is a partial solar eclipse time lapse. So we also got to see a little part of the prominence and an eruption, so to speak, from the sun's surface. All right, so what would, if that's a solar eclipse, what's a lunar eclipse? Well, a lunar eclipse is where the earth blocks the light from the sun and the moon passes through earth shadow. So this is a little bit different effect. Of course, we're not looking at the sun. This occurs at midnight when the sun is behind us, behind the earth. And the shadow of the earth is extending out toward the moon. Okay. And of course, the full moon has to be near the ecliptic plane. The ecliptic being the orbital path of most of the planets. Right? It has to be near that. So the tilt has to be moving so that now the tilt puts it in that plane. Since the Earth's shadow is so much bigger than the moon's, the lunar eclipse can last for more than an hour and a half. And that's when the moon is in the Earth's umbra. But the total, I mean, the partial portions of the eclipse can last for 3 hours. As the moon moves into the penumbra, it actually kind of gets a little reddish color. Now, why is that? Remember when we were talking about bending light? Well, actually, it's not just bending, it's not just refraction, but the Earth's atmosphere absorbs the blue wavelengths of light and leaves the red. So the red is the light that makes it into the penumbra. And sometimes they call them blood moons because it's a deep red. And at this time, this is the best time to use the moon's, those retroreflectors on the moon to make measurements. That or, well, actually, the new moon wouldn't be such a good time either because you have lots of light scattering. So actually, this is the best time to use the retroreflectors and fire your lasers at them is during a lunar eclipse. There you go. So the moon takes a while to move through the penumbra. It gets into the umbra where it goes completely dark and then back out into the penumbra. Now, the moon is still moving around the Earth, and it's having a gravitational effect. It's pulling on the Earth. Okay. All right. So here's the Earth. Here's the moon. Right? And the moon is rotating around the Earth. And remember what I said about the center of rotation. In this system, the center of rotation is here, just off center. So the Earth is sort of wobbling as the moon travels around the Earth. Well, the surface of the Earth is not solid, not all of it. 2/3 of it is liquid surface. So you have water here. Okay? So liquids respond greater to gravitational forces than do solids. Right? The solid part of the Earth doesn't want to deform. It does a little bit, but not much. So what happens is when the moon's over here, you get a bulge. Right, like that. A bulge in the water. And as the Earth rotates, it rotates underneath that bulge. So that's where the tides come from. The water's not moving, the Earth is moving underneath the water. Now we also get a bulge on this side. Right? So why do we get a bulge on the opposite side? Let's see if I put a comment in there. So as early as the 1st century, people noticed the relationship between the moon and the tides. But at that time, no one could explain them. In the 17th century, Newton, Sir Isaac Newton, applied his law of universal gravitation to explain the ocean tides by the motions of the Earth, moon, and sun. I haven't invoked the sun yet, but it's involved too. Okay, so the moon is pulling on the water and the Earth. So as it does so, the Earth shifts a little bit. So that's what, the closer you are, the stronger the pull, right? So the stronger the pull here against the water brings it up, but it's also pulling on the Earth, which shifts the Earth over underneath this bulge and leaves some of the water behind over here because it's pulled less strongly. So that's why you have a bulge on this side and a bulge on that side. And as the Earth rotates, it rotates under both bulges. So there's going to be a high tide every 12 hours, actually 12 and a half hours. Two daily tides. Right, there you go. There's the explanation. All right. Now, that's every day. But periodically, we have extra high tides called spring tides. They occur, now we've got the sun involved. The sun is more massive than the moon, but it's farther away by about 93 million miles. But it still has an effect. And it's pulling on the earth and the water. So it tends to, when they're lined up like this, or when the moon's on this side, the combined gravitational effect gives you spring tides. They occur when the sun, moon, and the earth are all positioned in nearly a straight line. That's a spring tide. All right. Now, the high tides will be higher and the low tides will be lower, right? Because you're moving all this water out here, these areas here get lower. So they occur twice during each lunar month, at the new and the full moon. So they're predictable. We can predict the spring tides and the neap tides. When does the neap tide occur? Well, the neap tide occurs when the moon and the sun are in opposition. Not opposition like this, but when their gravitational effect opposes. So when you have the moon over here, or the moon over here, then you get pulling here and pulling there, and this tends to reduce the impact of the low tides, increase the height of the low tides, and decrease the height of the high tides. Those are neap tides, and they also occur twice a month. Those are when the high and the low tides are at the high tides at minimum and the low tides at maximum. Twice during each lunar month. And that's during the first quarter and the last quarter. Right? So here's an illustration. This would give you spring tides where everything's lined up. Either the moon's over here or the moon's over there. And then if they're right angles to one another, you get neap tides. Well, actually, the low tide is here toward the sun. The moon is closer, so it has a greater impact on the movement of water. So in that case, the bulges are on this side. Okay, those were the general types of tides. But tides also vary with other factors. Latitudes will affect the tides, and where the latitude is in relationship to the moon and the sun. Right? Is it tilted this way? Is it tilted that way? So there's that variability. So those tidal bulges will be highest for the latitude in which the moon is directly overhead, or where it's on the other side of the earth, opposite. So what effect does that have? If the spring tide occurs during the summer solstice, at 23.5 degrees north and 23.5 degrees south, you have an increased height of the tidal bulge due to the fact that the Earth, the moon, is overhead. And the sun is also opposite the moon, or on the same side as the moon. Now, it won't occur at 28.5 degrees because the Earth's tilt dictates where the sun is. So the sun position based on the tilt of the Earth has to line up with the moon. So that's why we can't use 28.5 degrees, has to be 23.5 degrees, north and south, during the summer solstice. And this is in the summer solstice here is referencing the northern hemisphere. And it's also valid for the winter solstice in the northern hemisphere, because that would be the southern hemisphere's summer solstice, right? So you see that the bulge on either side is impacted for the southern and the northern hemispheres. Okay, what is the effect on tides? The effect of tides on the Earth and the moon. These tidal cycles have been calculated to actually retard the Earth's rotation just ever so slightly. Slowing the Earth down at a rate of about 0.002 seconds per century. So it's not much, but obviously it's measurable. So that's 2 milliseconds per century. Now, over thousands and thousands and millions of years, that has an impact. The Earth used to spin a lot faster. The day used to be shorter than it is now. So, and the system, the angular momentum of the system must be conserved. So if the Earth is slowing down, the moon's angular momentum must increase. And the way the moon's angular momentum increases is not by speeding up its around the Earth, is by moving further away. Remember, you can have the same speed, velocity, instantaneous velocity around an orbit, but if it's further away, the angular momentum calculation increases by distance. So as the Earth slows down, the moon moves further away. So there may come a time when this tidal locking doesn't work anymore. The moon's orbit is increasing about 1.3 centimeters per year. So if we go backwards, right, work our way backwards based on what we know, 1 billion years, the solar day would have been 5.6 hours shorter than it is now. So that'd be 18.4 hours would be the length of the Earth's day. And the moon would have been 13,000 kilometers closer, right? All right, so now we're going to look at other moons. Mercury has no moons. That's an easy one. Venus has no moons. Earth has one. Mars has two. So we can look at the Mars because it's the only other terrestrial planet with moons. Phobos and Deimos. Right? Those are Greek words that mean fear and panic. Actually, they're related to Greek mythology, characters. Now, if we move out to the Jovian planets, Jupiter actually has more than 8, about 80. That's true. About 80 known moons. We're still discovering some. So the telescope was actually, we believe, invented by Hans Lippershey, who was a Dutch spectacle maker. He made glasses for people. Now, he may not have been the first one that came up with the idea, but he was the first one who applied for a patent for his construction of a telescope using lenses. He knew how to make lenses. There's a story behind it, but I'm already running long, so I'm just going to say he applied for a patent and it was denied because the Dutch authorities said it was not unique enough to be considered patentable. Well, all that did was made his patent application available to the rest of Europe, the rest of the world, and tinkerers all over the continent started making telescopes. One of those was Galileo. So it didn't take him but a couple of years, and he had made a telescope for himself, and he was observing the moon and Jupiter. And he identified 4 of the largest moons of Jupiter. That's why they're called the Galilean moons. And they are Io, Europa, Callisto, and Ganymede. Ganymede is the largest moon in the solar system. It's even bigger than our moon. The very latest moon, number 80, was actually identified by an amateur astronomer not too long ago, 3 years ago. So here are the 4 largest moons. There's Io. It appears to be very volcanic. Europa, covered in water. They think that this ice, which is several kilometers thick, underneath it is an ocean of water. We don't know yet. There's Callisto and there's Ganymede. Now, none of these moons have thick atmospheres. They may have some gases close to their surface, but they're not what we would consider a viable atmosphere, any more than we would say that Mars has a viable atmosphere. So this is a Ganymede and Jupiter flyby by the Juno spacecraft. It takes about 4 minutes to watch, but I think it's worth it. So let's take a look. All right. I love watching that. Oops. There we go. We don't have time to watch it again. So here are Jupiter's 4 largest moons, and there's some particulars about them. The largest one here, I believe, distance from Jupiter is the first indicator here. Io is the closest one. Callisto is the furthest away of the 4 Galilean moons. And just for reference, the Earth's moon is 384 kilometers from Earth, and Ganymede and Callisto are much, much farther away. Europa and Io are closer. The orbital period tells you something about their distance also. It only takes 1.77 days for Io to orbit Jupiter, whereas Callisto takes 16.7 days. And this has to do with the mass of Jupiter. It's huge. Diameters here. Right? Ganymede, there's the biggest one, 3,270 miles. Right, so it's maybe, what's that, 3/8, a little over 3/8 of the Earth's diameter. It's pretty big, bigger than the moon, obviously. Compared to the Earth's moon, if we set the mass of the moon, the Earth's moon, at 1, then Io is heavier. And Europa is not as heavy, probably because we think there's a lot of water there. Ganymede is much more dense, and Callisto is more dense. And then we have the density stated here. Remember, kilogram per cubic meter is, you move the decimal place 3 places to the left. So this will be 3.5 grams per cubic centimeter. If water is 1, then that's your comparison. All right, Saturn. Saturn has even more moons. This is Saturn's largest moon, Titan, and it is a big one. This picture was taken by the Cassini orbiter in 2004, that closest approach to Titan. Now, we've known about Titan for quite some time, right? Since 1655. Christian Huygens, was a Dutch astronomer, discovered Titan. And that's why the spacecraft is called Cassini-Huygens, named after this guy. The Cassini part is like the parent spacecraft, and Huygens is a separate lander that's attached to the side. And during one approach, this may have been this one, Huygens separated from Cassini on a trajectory toward landing on Titan, and it did. And I'll show you some of that in just a minute. So Titan is 50% larger in diameter than Earth's moon and 80% more massive. So it is the second largest moon in the solar system after Jupiter's Ganymede. And yeah, the second largest. That's right. It's bigger than our moon. So it's the second largest moon in the solar system. And it's the only one with a dense atmosphere. That's one of the reasons we wanted to go look at it. All right, so the Huygens lander separated from the parent vehicle on Christmas Day 2004. So let me go back just a second. Okay, so it was probably on this flyby that Huygens separated from the Cassini vehicle. But it took it a little while, right? It took it 19 days to eventually land on the surface. And it was there long enough to capture data through the atmosphere. And then when it landed, it was still broadcasting for a little less than an hour before the environment shut it down. It was a very harsh environment, in other words. This is what the lander looked like. This is a model of the lander. And I got a video I want to show you that was pieced together from pictures that were taken by the Huygens lander as it entered the atmosphere and down to landing. Here we go.
January 14th, 2005 begins with the Earth passing directly in between the Sun and Saturn, an opposition so perfect that it occurs maybe twice per millennium. Meanwhile, the Huygens probe, quietly entering the Saturnian system, is about to end its 7-year journey. As Huygens approaches, the inner planets cluster around the distant Sun. Saturn appears almost as large as Orion. A few moons are visible as white dots aligned with Saturn's rings, while Titan, its largest moon, is already well resolved. Huygens is destined for Titan, a mysterious world larger than the planet Mercury and shrouded by a thick brownish-orange atmosphere. The details of its surface have never been seen. Huygens' speed increases to near 6 kilometers per second. The Titan's disk quickly obscures our view of Saturn and its more intimate moons. As the probe enters Titan's atmosphere, the heat shield reduces the speed some 15-fold within a few minutes. The main parachute reduces the speed further. 15 minutes later, the smaller stabilizer chute allows a faster descent at first, but slows as Huygens enters the lower, denser parts of Titan's atmosphere. Huygens is approaching a dark valley between brighter, hilly regions. Beyond the hills to the left, 2 dark parallel lines appear, which are later discovered to be part of a vast system of dunes which surround the moon. At 21 kilometers altitude, the probe moves through a thin haze layer as seen on the horizon. The bright area near the center top is the glow of Titan's haze illuminated by the sun. A complicated system of drainage channels, some hundreds of meters wide and kilometers long, are seen cut into the hillside. These are probably the result of runoff from methane rain. Stereographic imagery reveals hills to the left to be perhaps a few hundred meters tall, while features in the valley are tens of meters in height. For most of the descent, the probe travels eastward above Titan's surface. However, below 7 kilometers altitude, the motion reverses into a backward westward motion. It reverses again at 1 kilometer altitude, and we move slowly southeastward. Hang on, as Huygens lands on Titan's surface near a water ice outcropping ridge. Another westward-looking view of the descent from 31 kilometers shows the area of Titan over which the probe has just flown. This affords us a good view of the drainage channels and apparent shoreline. More dark lowlands appear and a rough pitted hillside to the left. Spectra of the surface suggest that the bright areas are water ice, and the darker areas are a type of hydrocarbon mixture that has never been produced in the laboratory. The small white dot in the lower center part of scene tracks our progress over Titan's surface. We see the reversal of direction at 7 kilometers altitude, and we fly over the ridge near where we will land. As we approach the surface, our perspective brings the topography to life. We see that although there are rivers and a shoreline, the basin is dry. Below, there are distinct signs of erosion which crafted the rugged ridge line. Huygens sinks into one of these gullies. We experience a relatively soft landing on Titan's surface. The view from the surface reveals an amazingly Earth-like picture of a dry riverbed with distant hills which are a few meters in height. Some seconds after impact, the shadow of Huygens' parachute drifts across the sea. The heat from the surface science lamp in the probe's skin vaporizes methane from Titan's surface, which is about 180 centigrade degrees below freezing. Near the probe, the ground is littered with water ice rocks and smaller pebbles, which could be made of water ice, or hydrocarbons, or some combination thereof. Although we now know more than ever about this mysterious world, many questions remain unanswered. Where is the vast reservoir of liquid methane necessary to replenish the atmosphere? Where and how often does it rain on Titan? How does the methane get recirculated into the atmosphere? What materials make up the surface? What processes create and shape the hills, dunes, and valleys?
So the thing that puzzles me is during Huygens' descent, remember, the narrator says a direction change, drifting east and then drifting west. That tells me at that time, Huygens was on a parachute. That tells me that it was being influenced by winds in Titan's atmosphere. As it went through one layer, it got blown one way, and then it dropped down through another layer and blown back the other direction. Okay, so there are other moons. Some of them were photographed during Cassini's visit, and these are photographs from that visit. I don't think these are in any order of importance. I tried to put them, size their pictures for their relative size to Titan. So we got Rhea, Iapetus, Dione, Tethys, Mimas, and Enceladus. Enceladus is pretty interesting. We'll talk about that one in a minute. But I noticed that several of these, starting with Mimas, see that big crater? Tethys has a big crater. There are several craters on Dione, but they're not as big as these. Iapetus has a huge one. And here's one on Rhea. So my guess is that they probably experienced bombardment in a similar time frame to our moon. I don't know for sure, but I suspect that's true. Of course, Titan would have been protected by its atmosphere. Almost anything that tried to get through to the surface on Titan would have burned up in the atmosphere. Now let's look at the moons of Uranus. It's the next Jovian planet out. It has quite a few. Let's see. Did I put a number with that one? No, I just mentioned these are the 5 largest moons of Uranus. So compared to the Earth moon, this gives us some perspective. Compared to the Earth moon, they're all smaller, much smaller. Right, so they have names that probably mean something to the people that named them. Mythical characters, I imagine. But their densities are in the neighborhood of that of water. So what does that tell us? It tells us that since they're not, and we can go to the next frame, since they're not, they don't have lots of hydrogen and helium in their atmospheres like the gas giants, then we have to blame their low density on something else. And that means they probably got a lot of water in them, water ice. Right? And in relative size, Titania is the biggest one of this group. Miranda is the smallest one. And my guess is these were photographed probably by Voyager, because we haven't had a separate probe go to Uranus or Neptune and stay there. So these photographs had to be taken by flybys. And we get to Neptune. Triton is the largest of Neptune's moons. It has 13 of them. And this is the only one of the large moons to have a retrograde orbit. In other words, instead of clockwise looking down from the north, its orbit is counterclockwise, which tells me that Triton was probably captured by Neptune as it passed by. And this may very well be true of many of the other moons that we've seen so far of the Jovian planets. They were captured. And it would make sense considering their large gravity well that surrounds them. Now, the dwarf planets have moons also. Pluto has 3 of them. Right? Charon is the largest one. It's about half the size of Pluto. So it's pretty large. In fact, it's the largest satellite, the largest moon in relationship to the planet or dwarf planet. Which means that as they rotate, as the Charon moves in its orbit, the center of mass of that orbit is outside Pluto. So Pluto doesn't just wobble, it actually moves in its position as Charon moves around it. This might be considered a binary system. So, you know, which one's the parent and which one's the child? We generally take the bigger one, of course, as the parent. Now, these Charon and Pluto are tidally locked. In other words, Charon and Pluto always have the same faces toward each other. They're synchronous. Let's see. You know what? I misspoke. Pluto has 5 moons, not 3. That needs correction. There are 5 moons that belong to Pluto. And since all these pictures were taken by New Horizons when it flew by, that limited exposure, and it just depended on how close it was to the moons. It must have been pretty far away from Styx and Kerberos, because they're just fuzzy dots. But it got enough information to prove that these are all moons. Charon is the biggest, and these guys are just tiny. So they basically have little impact on the way that Charon and Pluto behave toward each other. Okay, the other dwarf planets. Ceres is in the asteroid belt, has no known moons. Makemake has no known moons. Eris has 1 known moon, Dysnomia. Don't know much about it. But Haumea, Makemake, and Eris are all trans-Neptunian objects. Ceres is the only one that's in the asteroid belt, classified as a dwarf planet. These others are out in the Kuiper belt. Haumea, though, has 2 moons, Namaka and Hi'iaka. That sounds Hawaiian to me. Okay. So let's talk about the water composition of the solar system, and why it's important. The composition of the moons of the dwarf planets is to a large percentage water ice. And I mentioned that earlier based upon their densities. The moons of the dwarf planets are probably captured objects from the Kuiper belt. But water is found other places. Some places that are surprising. Now, first of all, how do we know that that's water? Sometimes we do it by density, and we propose the presence of water. And then why does it matter? Various techniques offer clues and some hard evidence for the presence of ice in and on solar bodies, right? Photographic evidence. When we photograph something, we look at surface features. Some surface features can only be frozen objects, and in some cases we can discern icy objects simply by the way that they're formed. When we have probes that can go to the surface, we can sample, right? We've had probes land on comets, and they've sampled the surface and then returned those samples to Earth. Or, in one case, the Saturn's moon Enceladus was sampled remotely by the Cassini probe. In other words, features were noticed, things were noticed coming from the surface of Enceladus, and Cassini was retasked to sample those emissions from the surface of Enceladus. So they would have Cassini fly through the plume, right? It was a volcanic activity, but not molten rock. It was water that was being spewed out of the surface of Enceladus, and Cassini flew through it and sampled it. That's what I call a direct near-approach sampling, or a flyby sampling. Now, we can also get information from spectral analysis, right? We can analyze light being reflected from objects in space, and by analyzing their visible, their infrared, and their ultraviolet spectra, we can deduce that there's water there. We can also get radio emissions from them too. If they're active enough to form broadcast radio signals, sometimes we can deduce the presence of water there. Or we can fire radar at it, right? If it's cloudy surface, which would really be only valid for Titan, we can fire radar at the surface, and the return reflection will give us clues as to whether there's water there. The reflectivity also matters. Clouds in the atmosphere, like on Earth, or a reflectivity of ice, like on Enceladus. Enceladus is a very bright object. It has very high albedo, simply because it's covered in ice. All right, and then the average density I mentioned earlier can indicate presence of ice or water. Now, why does it matter? As far as we know, water is absolutely essential in any of its form, solid, liquid, or gas, for the existence of life. So anybody searching for life on other heavenly bodies will search for water first. The presence of water on other heavenly bodies also gives us clues as to how Earth acquired its water, because Earth history favors a waterless world, right? The Earth was too hot, especially if the large impactor theory for the formation of the moon is true, then that impact would have heated things up to such an extent that no water is left, and the moon is evidence of that. So it makes you wonder, how did Earth acquire all of its water? Well, one theory was that during a period of heavy bombardment, lots of the water was brought in on comets. Would have to be a lot of them, right, to make as much water as there is on the Earth. But that's one theory. And not just for Earth, but the analysis of water in other parts of the solar system helps give clues as to the formation of the solar system itself. Remember, we mentioned the oxygen isotope ratio. It doesn't have to be elemental oxygen. It can be oxygen as part of water molecules. That isotopic ratio is an indicator of how far away from the sun this particular object formed. It can also give indications relative to tectonics on other heavenly bodies as well as Earth. Once we've characterized the occurrence of water and the movement of water in the solar system, it helps us when we're searching for exoplanets, that is, planets orbiting other stars. It helps us understand something about those systems as well. So it all fits together. We try to fit it together into a coherent story. Okay, other small solar system bodies. Asteroids. Asteroid is a word that means star form. In other words, it appears as a star, but we know it's not a star. Meteoroids, meteors, and meteorites. They're all the same object depending on what the object does, right? So meteoroids are any object in the sky, in the space, that could potentially impact another heavenly body. Meteors are those that enter the atmosphere. And these are particularly in reference to the Earth. Meteors enter the atmosphere, and most of them burn up. And we see them in meteor showers. Some are rogue, and some of them are regular. They occur same time every year. And meteorites are those meteors that have enough mass to strike the Earth. Part of them burns up, but they have a core that makes it to the ground. That's a meteorite. Okay, comets. Comets are objects that have very elliptical orbits. They enter the solar system. Sometimes the orbit is elliptical, and I'll say more about this in a minute. But they're believed to come from either the Kuiper Belt or the Oort cloud. And then there's interplanetary dust. All right, let's say something about asteroids. Asteroids, most of the asteroids are located in the region between Mars and Jupiter. They're in orbit around the sun in that region. And most of them, well, there are actually three types, and we'll describe them in a second. Over 20,000 of them have names or numbers. So we've studied them and their orbits. But estimates are that there are millions of asteroids in that belt and in other places. And we'll mention those in a minute. About 100,000 of them are bright enough to be photographed by Earth-based telescopes. So that's quite a bit. Now, how do we know that they're out there and what they're doing? Well, if you photograph them and the stars behind them are reasonably fixed in their positions, then you take photographs, a series of photographs, and you look at them in comparison, and you see there's something up there that looks like a star, but it's moving, right? That's not a star. It has to be some other object. And if you watch it for several days in a row or several weeks in a row, however long it takes, and you can use that information to calculate its orbit based on Kepler's laws primarily. And once you define its orbit, then you know where it is. And most of those occur in the asteroid belt. Sometimes we call them minor planets. Ceres used to be a minor planet before the definition was changed, and now it's a dwarf planet. But it was originally discovered in 1801. Right, by that method I was mentioning. And it was obvious that it was discovered first because it's the biggest one, easiest to find. So Ceres is the biggest one, and the next largest that are still asteroids are Pallas and Vesta. This picture is a montage of the asteroids that have been visited by spacecraft. All right, so we have this one, Lutetia. We have others. The only one that's not an asteroid is this one right here, Halley. So we actually had a spacecraft visit Halley's Comet the last time it came through. But Pallas and Vesta are not there. Right? Several have been visited by spacecraft, but Pallas and Vesta have not. Even though they're the largest, I suspect it was because they were not in the proper position for spacecraft to reach them. We didn't have time to get ready for them. So we'll eventually go out there, I'm sure. Or one of our spacecraft will go out there. So asteroids can be classified based upon their composition. A C-class asteroid is called a chondrite, and it's primarily carbon-based materials, clays, and silicate rocks. So it's very dark. It's difficult to find. And they're located largely in the farthest edge of the belt. So if this is the orbit of Mars, and then Jupiter's way out here, and the asteroids are here. And this edge out here is the C-class. About 3.5 astronomical units from the sun. Very dark, primarily due to the carbon. And these are 75% of the known asteroids. That's most of them. Then there's a class called the stony ones. They're a little closer in. The S-class. There's basically silicate materials with some nickel iron mixed in with them. That's why they call them stony. They're like rocks. Could be considered, some of them are actually rubble piles. Very loosely held together by weak gravity. They're in the middle of the belt, it's about 2.5 astronomical units. They're brighter than the sea, right? Because the material that they're made of. And that's about 17% of the known asteroids. And then the last group are the metallics. And they're in this region. In the inner belt. Right, so in, less than 2 astronomical units. Remember, Mars is orbiting at about 1.35 astronomical units. So they're not really close to Mars. They're closer to Mars than they are to Earth, but they're still pretty far out there. And this is about 8% of them. Okay. We can also classify asteroids as main belt, that is, those in here. They stay in their orbits between Mars and Jupiter. Or Trojans. They orbit in regions that are occupied by an existing planet. Right? We might have 1 or 2 in Earth's orbit. But fortunately, these asteroids are positioned at one of the Lagrange points. So they're not a threat to the planet. Now, I'm going to explain what Lagrange points are in just a second. The other possibility is orbit crossing asteroids. Those are the dangerous ones. They could be near-Earth objects. So that's why we are surveying the skies as best we can to find these asteroids as soon as possible. The sooner you find an approaching object from space, asteroids, comets, the sooner you have, the longer you have time to do something about it. The sooner you find them, the farther they are away from you, the less effort it takes to change their orbit so that they don't strike the Earth. And these near Earth, which really is a subclass of orbit crossing, these near Earth objects. And when they say near Earth, they could be out 2 or 3 times the distance to the moon and still be considered near Earth. We try to track those and monitor them very closely. There's a scale that's used to assess the threat to the Earth of any of these objects. It's called the Torino scale. And I'll bring that up in just a minute. I want to look at one other thing first. What's a Lagrange point? Well, to make a long story short, there were actually 2 mathematicians. I forget the first one's name, but Louis Lagrange took the work of this other mathematician who said that there were points in the around the or in the orbits between 2 large objects, like in this case Earth and the Sun. So that's your system, Earth-Sun system. See, let me get over here. Earth-Sun system. And he said that there were points where objects could sit there in relation to these 2 objects and just remain there all the way around in those positions. Normally, if this was an independent orbiting object around the Sun, it would be moving faster. So it would be here one day and then be over here, and the Earth would lag behind it. But the gravitational effect of the Earth and the Sun keeps that object there. Other 2 points are on the opposite side of the Earth at the same distance as L1. And then there's one on the opposite side of the Sun over here in the Earth's orbit. Now, what Lagrange said was that there are 2 other positions also that he calculated, L4 and L5, right? 4 and 5. Now, what's the difference? It's an important difference. L1, 2, and 3, initially identified, are metastable. That means if you want to position anything in those points, whether it's naturally occurring or we want to put a satellite out there, then those are metastable positions. In other words, they're sort of stable temporarily, but it's easy for them to lose their lock in those positions. So if we want to put something out there like we've got the James Webb Space Telescope built and ready to go, and it's going to be positioned at this L2 point way out here. That's because it's an infrared telescope, and it needs to be farther away from the Sun with special shielding on it in order to observe the universe in the infrared. But when it gets out there, it's got to have fuel. It's got to have enough fuel to make orbital adjustments and keep it near that position. That's because it's a metastable position. If we just sent it out there, it might sit there for a little while, but eventually it would lose its position and just fly off into a different orbit. However, L4 and L5 are stable positions. They're stable Lagrange points. Any object at these points will be stable with respect to the other object, the main object in that, say, planet, in that orbit. So these Trojan asteroids located in those positions are there to stay. They're not going to get closer to us. They're not going to get farther away from us. They're just going to sit there. And any of those in or near that position are no threat to the planet. So here's a model, right? There's Mars, there's the asteroid belt, and there's Jupiter way out there. It's important to recognize that Mars has a substantial gravity. Jupiter has a massive gravity effect. It has a pull on these asteroids. And when they pass, they can be thrown out of their orbit and could intersect our orbit at some point. Now, what's the origin of the asteroid belt? Nobody really knows. We have theories. One theory is that it was attributed to the breakup of a former planet. There had been a planet in that position and it broke up for some reason, either impact or gravitational effect from Jupiter, something. Because the Jovian planets, most of the planets, as a matter of fact, it's believed that they're not in the same orbit they were when they formed. And the Jovian planets may at one time formed further out and then moved in. But that's another topic. Trouble is, when we estimate the total mass of the asteroids in the belt, it's less than the mass of an ordinary planet, what we would consider an ordinary planet, even a dwarf planet. So that theory is kind of set aside. A more plausible explanation is that these asteroids were debris from the formation of the solar system that never formed into a planet. Now, why would that be? Well, in order for large bodies to form, they have to meet one another. They have to impact. But the gravity's so low, if they hit too hard, they'll just bounce off or they'll shatter. One or the other. Shatter into pieces or bounce off. If they're moving slow enough relative to each other, then they can stick. They might hit and bounce a little bit, but they'll be under their influence, each other's influence, and they'll eventually stick together. So the massive gravitational effect of Jupiter may have stirred up this nearby debris to such an extent that the velocities, the kinetic energies of these particles was too high, and they could not coalesce into a planet. That seems more reasonable than the shattered planet hypothesis. And like I said before, Jupiter and sometimes Mars, they continue to disturb orbits. Okay, here's the Torino scale that rates the risk to the Earth of any object that might impact us. If it's 0 on the Torino scale, they have no likely consequences. Events, the likelihood of a collision is 0 or well below the chance that a random object will strike the Earth. And if it did, it'd be too small and burn up. So the risk is nil. Torino scale 1 are those possibilities that should be monitored closely. Chance of a collision is extremely unlikely, about the same as a random object striking Earth within the next few decades, but we want to watch them anyway. 2, 3, and 4 are events in the range of those possible events that are of concern. 2 would be the lowest concern. Collision is very unlikely. 3 would be a close encounter with greater than 1% chance of collision capable of causing destruction. So the object would become a meteorite. And 4s, this is 3 is The difference is 3 is localized destruction, 4 is regional destruction. Okay, so it basically has to do with the size of the object and its velocity, right? Because remember, the kinetic energy of the object is proportional to its mass and the square of its velocity. So if it's moving 20,000 miles an hour, it's 1 potential. But if that same object were moving 40,000 miles an hour, it'd be 4 times as destructive if it hit the ground, because it had that much more energy. Now we get to the threatening events, level 5. Okay, so we've got a close encounter possible with a significant threat of collision capable of causing regional devastation. Okay, so now we're going to have a close encounter with threat of collision, regional devastation. 6 would be global catastrophe. And 7 would not just be close encounter, but extremely significant threat of collision, which would also cause global catastrophe. Now, the last 3, 8, 9, and 10, there's certainty of collision. Okay, certainty of collision. Okay, that's the first criterion to be met. And then, how big is it and how fast is it going? If there's a certainty of collision, but it's only going to cause localized destruction, then it's an 8. And these events occur on Earth between every 50 to 1,000 years. Okay, so they happen fairly frequently. If it's a 9, then the collision would cause regional destruction. And these occur between 1,000 and 100,000 years. So they're not as likely. 10 is got to be the worst. Collision will happen. It will cause global catastrophe. But these events, fortunately, happen greater than 100,000 years apart. So this collision probably has not been seen, I'm pretty sure, it hasn't been seen in human history, for sure. All right. Now let's go to meteoroids, meteors, and meteorites. I sort of defined them, but this is in black and white. Meteoroid, any interplanetary metallic or stony object. Could be ranging in size from sub-millimeter to hundreds of meters, with the potential to collide with another object. So that's basically everything. That's not a planet, a dwarf planet, an asteroid, or a moon. Or a comet. We haven't defined comets yet. A meteor is a meteoroid that enters the Earth's atmosphere. Now, I would argue that it could also enter the atmosphere of some other planet and be considered a meteor. And that comes from a word that means shooting star, which is what they do, because meteors burn up in the atmosphere. Now, if it hits the ground, if the meteor hits the ground, it's a meteorite. Doesn't matter where the object came from. Could be a comet, could be an asteroid, could be other small body. And I guess that qualifies my earlier statement. So comets could be considered meteors or meteorites. So here's an example of a regular meteor shower. Happens every year, exactly the same time. The Perseid meteor shower and the Leonid meteor shower. So there are 2 constellations in the sky, Perseus and Leo, the lion. Perseus is Greek mythology. Just read up on it. And the reason they're called Perseids or Leonid meteor showers is that from the Earth's surface, we have an atmosphere, and the meteors are coming in such a way that they appear to be coming from one of those constellations. So if Perseus is up here, that doesn't mean the shower is coming from Perseus. It appears to originate from Perseus. So to the observer on the surface here, it appears that a line drawn from the track of the meteor back to some common point points to Perseus. Or it could be Leo, either one. That's just the way meteor showers appear in the sky. Meteorite impacts, I've said it before and I'll say it again, most of the impacts throughout Earth's history have been erased by geologic activity or by water and wind erosion. Here's one example that still exists because it happened fairly recently, actually. This is the Barringer meteor crater in near Winslow, Arizona. Okay, it's believed to have happened about 50,000 years ago. Right, and the diameter of the crater is 3/4 of a mile across, so it's pretty big. And it's a depth of 560 feet. So that depth is based upon the surrounding terrain, not the rim. The depth from the surrounding terrain, flat surrounding terrain, to the bottom is 560 meters. And then the rim rises about 150 feet above the surrounding terrain. How big was the meteorite that hit? Well, pieces have been found of it, but the whole thing, no, because much of it was destroyed and flung out of the crater when it struck. It's known that it was an iron composition, and fragments have been recovered. So the estimate is that it was 160 feet across, about 50 meters. So it's pretty big. How about comets? Relative to most asteroids and some meteors, comets are relatively small objects. They're composed of dust and ice and whatever else possible, which is why they're called dirty snowballs. And most of the time, they have highly elliptical orbits. Right, so when they come in, by the time we see them, they're usually within the orbit of Jupiter. Unless we've seen them before and they're on a regular trajectory and we know they're coming back, then we can look for them, like Halley's Comet. But they're named after this term here, long-haired star, Aster Cometus, which is Greek for long-haired star. And they're named that for a reason, because of the tail. That's their long hair. Now, these comets cannot disobey Kepler's second law of planetary motion, which means as they approach the sun is at one focus of their ellipse. Then as they approach and get closer and closer, they have to sweep out the same area over the same period of time. And in order to do that, when they get close, they have to move faster. So their highest velocity is at their nearest approach to the sun, the perihelion. That's their maximum speed. Their minimum speed is at aphelion, the furthest away from the sun. Okay. Some of the long period comets, They have periods of hundreds of thousands of years. And there are a few that we've identified must have hyperbolic trajectories. And remember what a hyperbola does. You don't know where it came from. You don't know where it's going. It comes in and it's gone. You only see it once and never see it again. Okay. But those are rare. It's believed that they may originate in the Kuiper Belt, out trans-Neptunian, or in the Oort cloud, way out there. The Oort cloud is probably not influenced so much by the Jovian planets as it is by passing stars. It's far enough out there that other objects that we don't even know of, we haven't found, could disturb their orbits and send them into the inner solar system. Now, comets have structure, definite structure, basically 4 parts. There's a nucleus. It's typically a few kilometers or less in diameter, right? So on astronomical scale, that's pretty small. Composed of rocky or metallic materials mixed with ices of water, methane, ammonia, carbon dioxide. All of those have been identified in comets, spectroscopically speaking. There's the coma. Coma is the, I don't know if it's Greek or Latin word for head, but that's the head of the comet. Surrounds the nucleus. It's several hundred kilometers in diameter. Right? And it's formed from outgassing from the nucleus as the comet approaches the sun. The solar winds are blasting out all the time, and they're striking this comet that's moving pretty fast and getting faster. And the interaction of the solar wind with the nucleus starts more outgassing, and it forms this coma. And then, of course, part of the coma, it gets blown back away from the solar wind and forms the tail. It has very large volume, even though it's very tenuous. Its density is very low. It has a long, voluminous tail composed of ionized molecules and dust. And it can be millions of kilometers in length. And it gets longer the closer it gets to the sun, because the solar wind is stronger there, causes more outgassing. And then there's something else that's been identified, flybys and spectroscopic analysis. There's a hydrogen cloud that surrounds the coma. So it's even further out than several hundred kilometers in diameter. It's bigger than that. And it's believed that this hydrogen cloud is due to dissociation of water molecules from the nucleus. Now, I don't doubt that, but it begs the question, if that's the hydrogen cloud, what happened to the oxygen? It must have got blown away, right? Who knows? That's something for you to investigate if you're going to be an astronomer. So here we have this is actually a photograph of a comet. I don't know which one. There's the nucleus, there's the coma, there's the tail, and there's the hydrogen cloud. Okay, it's important to recognize that when you're looking at a comet, if you follow the tail down to the head and keep going, eventually you'll find the sun. So the comet is always pointing at the sun, even though its direction is not the same. That's because the sun, the solar wind from the sun, is responsible for forming these structures in the comet. So this is Halley's Comet. Yeah, these pictures were taken in 1910. So, April is coming in pretty fast, getting faster and faster, and the tail is getting bigger and bigger. Tail is huge by the time it gets to its closest approach, and then it fades away. Okay. I got to see Halley's Comet, 1986. So I was 23. No, 33. And it was a sight. It's not going to be back for another 76 years. Right? So I have to miss that one. That would put it here in 2162. No, 2062, excuse me. 76 years. 2062. All right, here's another comet that's very interesting, called Shoemaker-Levy 9. I take it that these astronomers, Carolyn and Eugene Shoemaker and David Levy, collaborated for years, and they identified several comets, and this was the 9th one. But they were very persistent. You have to be patient when you're looking for heavenly objects like this. But on the night of March 24th, 1993, these astronomers were using the 18-inch Schmidt telescope at the Palomar Observatory in California. A Schmidt telescope is a type of reflecting telescope that's designed to photograph large areas of the sky. That's take too long to describe it, the construction of various telescopes now, so I'm going to pass on that and just get to the meat here. So in the photographs that they took at that time, they discovered this new comet, Shoemaker-Levy 9. And the odd thing about it was, when they discovered it, it was not in a heliocentric orbit. That is, it wasn't orbiting the sun. It was producing a tail, but it was orbiting Jupiter. So they did a little, they observed it several times, calculated its orbit and trajectories, and back figured, and the estimate was sometime in the 1960s or 1970s, this comet approached Jupiter too close and was captured into a very eccentric orbit around Jupiter. And they just happened to see it here at this time in 1993. And it had a period of about 2 years. So it took it 2 years to orbit Jupiter. So between this observation and the next observation, it was going to come close to the planet again. Well, actually, by the time they saw it, it had already come too close to Jupiter. Remember, we talked about the Roche limit. How close can an object be to a planet and still retain its structure? That was one of the explanations for the rings around Saturn. The moons in that area were just too close to Saturn and they got ripped apart. Well, this comet, sometime in 1992, came too close to Jupiter. They say within 40,000 kilometers of the cloud tops, which was inside the orbit of the closest moon. And the gravity was just too great. It was inside the Roche limit, tore it into 21 separate pieces. So by the time the Shoemakers and Levy observed and photographed it, it was already starting to fly apart into a long string of separate pieces. And we knew it was a comet because each one of those pieces had a tail. Okay. It was predicted by the observations that were made by the Shoemakers and Levy and by others that were interested now once they made the announcement. They predicted that these pieces would not survive another encounter with Jupiter. In other words, their orbit had been changed in such a way that about this time, July of 1994, those pieces would actually strike the planet. And they did. Between the 16th and the 22nd of July, 1994, all 21 of those pieces struck the southern hemisphere of Jupiter. And the whole world was getting ready to observe it. They had enough time in advance. So they got the Hubble Space Telescope. They got a couple of spacecrafts that were headed out to do other things. They got them to turn their cameras on it. And lots of Earth-based cameras were also pointed toward this event. Interestingly enough, there was significant amount of energy contained in this comet because the readings that were taken from the impact sites said that the temperatures rose to as high as 24,000 Kelvin. That's extremely hot. And the plumes from the impact rose 300 kilometers above the cloud tops before they fell back down. So I'm going to show you some pictures and a video here in a second. They analyzed the ejected material from these impact sites, and they found lots of sulfur compounds. Elemental sulfur, carbon disulfide, hydrogen sulfide. They also found ammonia, helium, hydrogen, of course, that was to be expected. They found a little bit of methane and hydrogen cyanide. Now, some of these, well, the sulfur compounds didn't come from the comet's pieces. But some of these also might have been contributed by the comet. They did notice heavier elements in the plume, and those would have been attributed to the comet's nucleus, definitely, because they couldn't have come from the atmosphere of Jupiter. All right, here we go. This is a photograph of the of some of the pieces. I don't know if they're all 21 there. Yep, they're all there, all 21 pieces. And notice that the bigger ones have huge tails, right? So this was definitely a comet. And now, let's see. Oh, this is another picture. These are scars left behind from the impacts. Most of the impacts took place out of view. So we had to see them when they came around. We saw what was left of the impact. Plus, we could measure the plumes on the limb, on the edge of Jupiter's disk. We could measure the height. Okay, have I got a video coming up? Here it is. Okay, now this is not an actual series of photographs. This is an artist's idea of what the orbit and impacts would have looked like in time lapse. And these are the times up here that are given, -3 days and then beyond. Okay. You notice each one of those pieces was given a letter in the order that it was going to impact the surface of Jupiter. Okay, now, last but not least, let's turn our attention to micrometeoroids and interplanetary dust. There's lots of dust out there. It's not very dense, of course, but it's still there. So when you say empty space, it's usually not right. Especially not within a solar system. There's plenty of dust left over from the formation. How do we know the dust is out there? We can speculate, but there's actually proof. One is called zodiacal light. This is a faint band of light along the zodiac. Remember what the zodiac was? So I put this refresher down here for you. The zodiac is a band on the celestial sphere, plus or minus 8 degrees, from the track of the sun. So the sun goes across here. That tells you where the center of the celestial sphere, the zodiac, is located. And on either side, about 8 degrees, is an area where you'll find all of the planets. You'll find our moon, because it's only 5 degrees inclined. All the planets and many prominent constellations, particularly the constellations that figure in astrology. And in that area, you will see light, reflected sunlight off of the dust in that region. And why is the dust heavier there? Because it's in the plane of the solar system. So all the leftover dust is right there. That's where you'll see it. This is fairly easy to find. This one is a little more difficult. The Gegenschein, which is a German word for counterglow. This is also due to reflected sunlight, but it's only observed when the sun is at 180 degrees from the observer and his night sky. And it's a diffuse oval spot. That's it. That's where the sun is coming around the earth and bouncing off the dust. I've got pictures here to show you. Here we go. So this is the zodiacal light here. Right there. See, there's Venus. It's right in the middle of it. Pleiades are prominent right there. It's not in the same position as the Milky Way galaxy, right? You'll see that, and that's very prominent. That's the plane of the galaxy that you're looking through. And then the Gegenschein here is observed in a very dark sky in the Andes Mountains of Chile at the Paranal Observatory, right? So it's more or less an oval-shaped counterglow. And the sun, in this case, would be exactly 180 degrees behind you. Okay, I think that's probably the end of the story. Okay, that was chapter 17. One more chapter to go. Chapter 18.